Okay, we are going to look at simulation. Is an agent approach of simulation where bacteria is act as an object. You are asked to develop a Python program to simulate and analyze the growth dynamic of bacteria colony in a grid-based nutrient environment. So you apply a object-oriented programming, random processes, and data visualization to model the dynamic of the system. So the project will involve moving a bacteria in a grid containing randomly placed a nutrient. Each bacterium has a chance to move towards a nutrient, reproduce, die based on predefined probabilities, and the simulation will track the number of bacteria over time. And you need to run a multiple number simulation to analyze the variability of the bacteria population dynamic. So we need to use a NumPy, MATLAB library, and random library in order to do this simulation. You need to understand the concept of object-oriented programming in this case. And here are the parameters. The simulation parameter is 100 times 100. Initially, you have 25 counts of bacteria. And nutrient count is 10, where 10 different nutrients are randomly placed in the grid. And each nutrient has a bite capacity of 100. If the bacteria bite one of it, 100 become 99. So bacteria also can die. So you have 1% probability of dying after 500 steps. You also have a probability of reproduction of 50%. That 50% only happen when immediately after it bite a nutrient. So you have a 80% of probability of moving towards a nutrient. So you need to initiate the grid. The grid represents the environment, and you randomly place a nutrient in the grid. So you need to define a bacterium class with method of movement, reproduction, and death. The simulation logic must include move towards nutrients, reproduce, and die. You need to run simulation, multiple simulation. So in your simulation, you need to run simulation such that all the bacteria have died or maximum step are reached. Here we just want to make sure that all bacteria die. The set could be like a few thousand. And you ask to do data visualization. So plot number of bacteria over time for each simulation. You can initiate the environment using grid NumPy. Create a bacteria class. Called bacteria class must have properties of position, of course, x, y, number of steps taken, and other method involved about the state of bacteria. You also ask to find the number of bacteria inside a grid. You ask to do the simulation, whether bacteria decide to move randomly or towards the nutrient. Then first you see whether your single simulation is correct, then you can run multiple of it. An example of output is something like this. So the simulation stopped when all the bacteria had died. So look at the program. I'll put all the parameters here. And the grid size 100, the number of bacteria, initially 25, number of nutrient 10, bite nutrient capacity is 100, death probability is 1%, reproduce probability 50%, move towards a nutrient probability is 80%, maximum step 500, the step before the death probability initiated, number of simulation I will do is 10. So I start with a class bacterium. So I initiate the bacterium with attitude of x and y, and step is starting 0. If you move random, then the coordinate x and y are given by the random choice, either whether 0 remain, 1 or -1 for x, and the same thing for y. One of the 9 possible cells. So, and then it wrap around the grid. If it is at the end of the grid, it will wrap back to itself. It's like become a periodic city of system. So from the extreme right, then you will go beyond the boundary, you will come to the extreme left, another boundary. So move towards the neutrons. So you attempt to move towards the neutron containing neighboring cell, because in this case, I did not specify exactly how the bacteria is going to move towards the neutron. So in here, we will check whether the neighboring cells, okay, defined by the 4 orthogonal neighbors, to see whether it contains neutrons or no neutrons. So I'll check one by one with boundary condition, the periodic condition. So if neutron exists, okay, so this grid will be greater than 0. I get distance from is the nx, and cell is the best distance. Here, initial best distance infinity. It's less than that, then the best distance is equal to distance. Then best move would be nx and y of one of the 4 choices. Here is a bit redundant because the distance is always 1, but we put it here so that later we can extend it to be a more general condition of how the bacteria move towards the nutrient. So here I get the best move. So if best move is true, then it will check whether is want to move towards a nutrient, because there's, so if you move towards the nutrient, then you will get the best move, else random, because we stick here, yes, 80% chance of move towards the neutron cell. So we need to add this. If no neutron found, so it moves randomly. Then I need to execute the move. So cell dot move towards neutron, whether best move or move, the step will increase by 1. Here I track the number of steps the bacteria have taken. So if check whether it's going to die or whether the bacteria die due to aging or randomness. So if cell state is greater than 500, so I got 1% of dying. Okay. So else is not greater, then it will be false. So reproduce. So the bacteria reproduce with fixed probability, spawn a new bacterium in a random agent cell. So I put the probability here, then if it is true, then you will execute this. Okay. And a new bacteria list, a new bacteria is appended to the list. So here I have a list of bacteria. Okay, let us look at the simulation. So initial grid, the grid all 0, okay, all should be integer, and then you fill the grid with a random number. Of byte size, byte neutrons. Okay, this will place your neutron randomly, because here I select randomly the coordinate x and y and place a neutron that will return the grid. Then run a simulation. I initiate the grid. Okay. I create a bacterial list. The bacteria are located in x and y position randomly. I create a list of 25 bacteria, because initial number of bacteria is 25. So you get a list of random placed bacteria here. Here I got a list that track the population size of each step. So while all the bacteria in the list, so population history will be a length of it, because will be 25, append it. Here also I create a new bacterial list, because it will reproduce later. So now it's empty. So while there is bacteria inside a list, it will loop until there is no more bacteria. For each bacteria in the list, the bacteria need to move. So after it move, I check whether it's going to die or not. Okay. So if bacteria die, we do not need to add in the next iteration. So here I check whether the bacteria is in the neutron location, because the grid size contain the neutron location and also the amount of neutrons there. So this is location of bacteria. So it's greater than 0. It's true, it is at location of the neutron, so that neutron locations consume, so -1. Also, because consume, it tend to reproduce. Okay, bacterium reproduce with a new list here. Initially is empty, so come here, it reproduce, then it will append inside the new list. So new bacterial list append. After you look whole things, okay, you want to see how many bacteria alive, dead, or have been reproduced add on. So you, for new bacterial list, you update it to the old list. Here, run simulation, return to population history. So population will keep update for each loop until all the bacteria has died. So I need to run multiple simulation. So run simulation for in range of number simulation. And then I plot the graph. Okay. This is plot the result. And then ask all are just a function and class. So I go for the main entry point for the simulation. So I run simulation, multiple simulation. Okay, call this one how many run, then plot the result of all the simulation. Okay, the same graph. So I got profile here. Okay, this profile help me to find how much memories are required in this kind of simulations. So when run, it takes less than a minute to get the result. So this is the result we get. You can see that even after 500, it's not necessarily drop. It can still increase, then decrease.